and heliospheric observatory, which is an orbiting observatory, and the Swan instrument, which stands for solar, wind, and isotropies. There's a big circle around the sun so it can pick up other things near it at the same time it's doing its job of trying to detect solar activity.
Space just got a whole lot stranger. Recent observations from the powerful James Webb Space Telescope have thrown the scientific community into a whirlwind, delivering data that many are still struggling to grasp. The culprit? Comet Swan, a long-period visitor, and the notorious interstellar object 3I/ATLAS. You see, the thing nobody tells you is that despite their vastly different journeys, Webb's astonishing detail has hinted at a mysterious, almost impossible connection between these two cosmic wanderers. This isn't just about rocks and ice. It's about a shared secret whispered across billions of miles, forcing astronomers to rethink everything they thought they knew about our universe's cometary residents. What shocking truth lies beneath these icy surfaces? Unsettling similarities. The initial data poured in, raw and undeniable, and the air crackled with a mix of excitement and disbelief in labs across the globe. When the James Webb Space Telescope turned its magnificent golden mirrors toward Comet Swan, officially known as C/2025 R2 Swan, and then to the interstellar enigma designated 3I/ATLAS, what it saw was a complete shock. Scientists, seasoned veterans with decades gazing at the cosmos, found themselves utterly stunned. This wasn't just another pretty picture from space. This was a riddle wrapped in ice and dust, suggesting a connection that, by all known rules of astronomy, simply should not exist. Many people are crazy about the James Webb for its ability to peer back to the dawn of time, showing us the first stars and galaxies. But it's also a master at detailing objects much closer to home, like comets, by looking at their chemical makeup in infrared light. This is where the real wow factor comes in. The Webb telescope doesn't just see things, it analyzes them with an incredible level of detail. It can pick out specific molecules like carbon dioxide or water, even in tiny amounts. When it did this for both Comet Swan and 3I/ATLAS, the findings sent tremors through the astronomical community. Let's talk about 3I/ATLAS first, because it was already a head-scratcher. Discovered in July 2025 by the Atlas Survey, this comet is special. It's not from our solar system. That's right, it's an interstellar visitor, meaning it formed around another star, somewhere out in the vast Milky Way galaxy. Only two others like it have ever been spotted before, Oumuamua in 2017 and 2I/Borisov in 2019. 3I Atlas is zipping through our solar system at an unbelievable speed, over 130,000 miles per hour, or about 21 miles per second. To put it mildly, that's faster than any comet we've ever seen pass through our neighborhood, and it's a huge clue that it's just passing by, never to return. Its path is what scientists call hyperbolic, meaning it's not looping around our sun like our local comets do. It's just making a quick one-time visit before heading back into the cosmic dark. The James Webb's early observations of 3I/ATLAS revealed some truly astounding details about its guts, so to speak. It showed that this interstellar traveler is unusually rich in carbon dioxide. When Webb looked at the ratio of carbon dioxide to water ice, it was literally off the charts, one of the highest ever recorded in any comet. This means it might have formed in a very different, colder environment than our solar system's comets. Or perhaps it experienced intense radiation that boiled away other lighter ices. This discovery alone was groundbreaking, offering a rare glimpse into the building blocks of planets and stars far, far away. Now, here's where Swan comes into the picture. Comet C/2025 R2 Swan was discovered in September 2025 by the Swan instrument on the SOHO spacecraft. Unlike 3I Atlas, Swan is a long-period comet, meaning it does belong to our solar system, but it takes hundreds, even thousands of years to orbit the sun. It comes from the Kuiper belt, or maybe even the Oort cloud, the icy shell that surrounds our solar system billions of miles out. Its path, though elongated, is still bound by the sun's gravity. When Webb observed Swan, scientists expected to see the usual mix of water ice and other common cometary compounds. But what they found instead was bewildering. The Webb data on Swan showed an unexpected significant presence of carbon dioxide, similar in proportion to what was seen in 3 IATLAS. Not just a little bit, but enough to make seasoned astronomers scratch their heads. How could a comet born in our own solar system, even from its far reaches, share such a peculiar carbon dioxide-rich signature with an object that originated from another star system entirely? This was the mysterious connection that shocked everyone. The composition shouldn't match up so closely if their birthplaces were so dramatically different. This isn't to say their trajectories are the same. They are definitely not. One came from deep galactic space, the other from our cosmic backyard. But the chemical fingerprint, the inner workings revealed by James Webb's infrared eyes, suggested an uncanny shared characteristic. It was like finding two people on opposite sides of the planet, both with a super rare, identical genetic marker that no one expected. This wasn't just interesting. It was a cosmic anomaly, a glitch in the matrix of cometary science. This perplexing discovery meant that either our understanding of comet formation was incomplete, or there was a deeper, more subtle cosmic process at play, one that transcended the boundaries of individual star systems. The most shocking fact is that this unexpected compositional similarity challenged long-held beliefs about how these icy travelers form and evolve. The implications were huge. If two comets from such different origins could look so much alike on a molecular level, what did that say about the universality of star and planet formation? Were the building blocks of protoplanetary disks, the swirling nurseries where stars and planets are born, more similar across the galaxy than previously thought? This shocking revelation from the James Webb Space Telescope wasn't just a fleeting observation. It was an urgent call for a complete reevaluation of cometary science. The search for answers began, driven by the sheer what-if of it all. This initial shock quickly turned into a frantic scramble for more data. But what could explain this impossible kinship? The truth might be even stranger than imagined. The alien visitor's deep secrets. 3 IATLAS, the original interstellar wanderer in this cosmic drama, holds deep secrets that continue to challenge our understanding of the universe. This comet didn't just appear from nowhere. It traveled light years, perhaps for billions of years, before gracing our solar system with its presence. Think about that for a second. A piece of a distant star system, a true alien visitor coming right to our doorstep. It's like finding a message in a bottle that's drifted across an entire ocean, only this bottle is a 7-mile-wide icy rock, hurtling at incredible speeds. The largest interstellar object seen yet. Its sheer size alone makes it a remarkable specimen. When it was first spotted, many people were crazy about the idea that it might be some kind of alien technology, much like the controversial suggestions surrounding Oumuamua. But scientists quickly confirmed it was indeed a comet, an active one spouting gases and dust. What made it stand out, even before Webb, was its early activity. Most comets from our own solar system only start to wake up and form a coma, that fuzzy halo, when they get closer to the Sun, typically inside Jupiter's orbit, which is about 500 million miles away. 3I Atlas started showing signs of activity much further out, suggesting its ices, especially that high carbon dioxide content, were much more volatile or easily released. The most shocking fact is that astronomers estimate 3I Atlas could be around 3 billion years older than our own 4.6 billion-year-old solar system. Imagine that. It's an ancient relic, a time capsule from the universe's past, carrying clues about conditions that existed long before our sun even formed. This incredible age, combined with its high velocity, suggests it gained momentum from gravitational slingshots as it whipped past countless stars and nebulas over eons. It has journeyed through interstellar space, the vast, empty regions between star systems, like a cosmic nomad. The James Webb's observations, specifically with its near-infrared spectrograph, provided invaluable insights into its chemical makeup. That dominant carbon dioxide signature isn't just a curiosity. It suggests that the comet's parent star system might have had a unique composition or experienced different processes during its formation. It's a direct peek into the nurseries of other stars, telling us about the temperatures, pressures, and available materials during their birth. What many overlooked before Webb's detailed gaze was how truly unique 3I Atlas's composition was compared to anything we'd ever studied. It wasn't just different, it was shockingly different. This interstellar messenger is literally a piece of another world, delivering information about stellar neighborhoods millions of miles away. It challenges us to expand our view of cosmic chemistry and the diversity of planetary systems out there. The idea that such an object could share a deep fundamental characteristic with a comet from our own cosmic backyard, as the Webb data suggested, amplified the mystery to new, dizzying heights. So while 3I Atlas is truly one of a kind in its interstellar journey, its apparent compositional twin from our own system raises an even more profound question: how could this be? A cosmic mirror. Comet Swan, or C/2025 R2, might be a local, but the James Webb Space Telescope has revealed that it's far from ordinary, holding its own hidden depths that echo the strange interstellar visitor. Unlike 3I Atlas, Swan calls our solar system home, emerging from its frozen, distant outskirts. It's classified as a long-period comet, meaning its orbit around the Sun takes hundreds of years. The longest tail ever seen on a comet belongs to Hyakutake in 1996, which stretched for an astonishing 350 million miles, twice the distance from the Earth to the Sun. Swan's tail, while not quite that extreme, has also been observed growing to an impressive length, sometimes 5 full moon diameters long in the sky. Discovered in September 2025 through images from the Solar Wind Anisotropes, or SWAN, camera on the SOHO spacecraft, this comet surprised observers with its rapid brightening. It reached an apparent magnitude of 6.2, making it potentially visible with binoculars under dark skies. Its closest approach to Earth is expected around October 20th, 2025, at a distance of about 24 million miles, quite a bit closer than 3I Atlas's nearest pass of 170 million miles. This close proximity offered an incredible opportunity for detailed observation, especially by advanced instruments like the James Webb. What many overlooked before Webb's data started coming in was the subtle hints that Swan wasn't just another typical long-period comet. Astronomers had seen variations in comet compositions before, but the consistent patterns were well established. Comets from the Oort cloud, for instance, are generally rich in water ice, which is what gives them their characteristic glowing tails and fuzzy comas as they approach the Sun. That's the normal script. But Webb's deep dive into Swan's gaseous envelope unveiled something else. Just like 3I Atlas, Swan exhibited a surprisingly high ratio of carbon dioxide. This was the what the heck moment that created the initial shock. For a comet born within our own solar system, this was highly unusual. It challenged the widely accepted models of how our solar system's icy bodies formed. You see, the closer to the Sun a comet formed in the early days of our solar system, the less likely it is to have retained a lot of supervolatile ices like carbon dioxide, which sublimate or turn directly into gas at very cold temperatures. So, how could a comet from our own Oort cloud have a chemical signature so remarkably similar to an object that traveled from another star? It suggested that the conditions in the farthest reaches of our solar system, where Swan was born, might have been far more exotic and complex than previously imagined, perhaps even mimicking, in some strange way, the chemical environments of entirely different star systems. This unexpected compositional similarity turned Swan from a fascinating local visitor into a cosmic mirror reflecting the perplexing characteristics of an alien from beyond. This bizarre parallel between the carbon dioxide levels in both Swan and 3I Atlas points to a potential unseen hand in their formation or evolution. It forces us to ask, are these just cosmic coincidences? Or is there a grander, more interconnected story to be told about the universe's comets? Beyond the known. The baffling compositional similarities between Comet Swan and 3I/Atlas, highlighted by James Webb's data, pushed scientists into a realm of deep speculation. This wasn't just a simple puzzle, it was a cosmic coincidence that defied easy answers. How could a long-period comet from our solar system's icy fringes and an interstellar visitor from untold light-years away possess such a similar chemical fingerprint, especially a high carbon dioxide signature? Many people are crazy about finding patterns in the universe, but this one felt almost too perfect, almost too designed. One possibility, a truly mind-bending idea, is that both comets, despite their distinct origins, might have formed under remarkably similar environmental conditions in their respective stellar nurseries. Imagine two separate star systems, billions of miles apart, forming in regions of their galaxies that just happen to have an abundance of cold, carbon dioxide-rich gas clouds. This would mean that the specific processes that lead to comet formation, the gathering of dust and ice in a protoplanetary disk, might be more universal than once thought, or that certain chemical mixtures are more robust in survival across the vastness of space and time. Another, more intriguing but still highly speculative idea centers on the possibility of a shared ancient event. Could both comets have passed through a common, perhaps incredibly dense or chemically unique, region of the Milky Way galaxy at some point in their unimaginably long histories? While 3I Atlas is known to be interstellar and Swan is from our Oort cloud, the Oort cloud itself is thought to be influenced by passing stars and molecular clouds over eons. It's not a completely isolated bubble. Perhaps a galactic flyby or a long-past encounter with a chemically distinct nebula could have seeded or altered the outer layers of both objects, giving them this unusual shared signature. This would be a remarkable case of cosmic convergence. The thing nobody tells you is just how difficult it is to trace the true origins of comets, especially those that have traveled for billions of years. 3I/ATLAS, for example, is estimated to be incredibly old. It's been wandering the galaxy, gaining speed from countless gravitational nudges. Pinpointing its exact birth star is nearly impossible. Similarly, while Swan is technically part of our solar system, its journey from the Oort cloud to its current position is still a long, complex tale of gravitational pushes and pulls. The most shocking fact here is that even with our most advanced telescopes, the universe still holds these profound mysteries close. Scientists are now exploring if there could be a previously overlooked mechanism that could lead to such high carbon dioxide ratios in both interstellar and long-period comets. Could radiation exposure play a larger role than we understood, perhaps processing the original ice compositions in unexpected ways? Or maybe, just maybe, some comets, regardless of their immediate birthplace, retain a core of primordial material that consistently shows this carbon dioxide richness, making them cosmic fossils of the earliest, coldest planetary building blocks. This isn't a settled debate, it's a wide-open field of inquiry. The James Webb data opened up a Pandora's box of cosmic questions, forcing astronomers to connect dots across unimaginable distances and timescales. The idea of a shared origin, whether through ancient formation conditions or a forgotten galactic encounter, remains a thrilling, if unproven, possibility. It reminds us that our cosmic neighborhood is far more dynamic than it seems, holding secrets that stretch back to the very beginnings of the galaxy. This deep mystery truly forces us to reconsider the vast, interconnected tapestry of our universe. What we still don't know. The journey to understand the bewildering connection between Comet Swan and 3I/ATLAS, as revealed by the James Webb Space Telescope, has brought us to a profound realization. The universe is far more intricate and surprising than we often give it credit for. While early, excited speculation might have hoped for a direct, dramatic link, perhaps a piece of 3I/ATLAS somehow breaking off and becoming Swan, the deeper scientific analysis quickly pointed to a more nuanced, and in many ways, even more fascinating truth. The truth is, scientific analysis has shown that the arrival directions of Swan and 3I/ATLAS are very different. Swan originated from the direction of the Aquarius constellation, while 3I Atlas came from Sagittarius, near the galactic center. This means they are not direct fragments of each other, nor did they follow the same recent path into our solar system. The immediate, dramatic connection of a single shared event in recent cosmic history, therefore, seems unlikely based on their trajectories. But not all things are what they seem, and this is where the real mystery lies. What the James Webb Space Telescope did show was a startling, undeniable similarity in their core chemistry, specifically their unusual richness in carbon dioxide. This is the wow factor that remains, the truly shocking fact that continues to puzzle scientists. If their physical journeys are so different, how can their inner workings be so alike? This forces us to look beyond mere celestial mechanics and delve into the fundamental processes of star and planet formation across the galaxy. One leading idea is that these compositional similarities might hint at a universal galactic blueprint for comet formation in extremely cold environments. You see, perhaps the conditions in the very outermost regions of protoplanetary disks, whether around our sun or another star, tend to produce comets with similar high concentrations of carbon dioxide. This would mean that the building blocks of icy worlds are not as unique to each star system as we once thought, but rather follow predictable patterns across the vastness of space. It's like finding similar ingredients in different kitchens worldwide. While the chefs are different, the basic components for certain dishes remain the same. Another perspective is that the early solar system from which Swan originates may have had more complex and diverse chemical gradients than current models fully capture. Perhaps pockets of material in the Oort cloud formed under conditions that truly mirrored the colder outer reaches of other star systems. This would mean that our own cosmic backyard holds more interstellar-like secrets than we realized. The most shocking fact is that even after extensive observations from Webb, Hubble, Gemini, and SPHEREX, the why behind this compositional kinship remains elusive. We have the data clear and stunning, but the full story of how these two distinct comets came to share such a peculiar trait is still being written. What many overlooked is the subtle yet profound implication that such similarities might point to universal laws governing the distribution of elements and the formation of icy bodies across the cosmos. It implies a deeper, more elegant order to the universe's chaotic dance of creation. This ongoing mystery makes us wonder, could these compositional similarities be more widespread than we currently understand, hinting at fundamental galactic processes we are only just beginning to uncover? Is it possible that the origins of these icy wanderers are connected in ways that transcend simple gravitational bonds, pointing to a much grander, shared cosmic history? The universe holds secrets beyond our wildest dreams. Do these cometary coincidences hint at a cosmic blueprint we're just glimpsing? Like and subscribe for more mind-bending space stories.